Hey there, yeah, so this video, what I'm going to do is I'm going to do a bit of show and tell on this robot sailing project that I have been playing around with for about 4 or 5 years now. And yeah, I want to clarify, this is not work, this is not school, this is just me playing around in the evenings and the weekends on this. And I think I'm motivated, mostly by the challenge. Like it's been a real challenge and it's really difficult. And I hope I'm going to get into some of the difficulties in this problem and sort of unpack it a bit. But it's pretty fun. Okay, let's get into it. So, what is this thing that I've been playing around with? So it's a stock radio control sailboat, and I have modified it so that it runs. It runs and sails by itself. So here we go. The boat has kind of an autopilot that decides where to go and steers the rudder and trims the sail. And it makes its own navigation decisions. So in this case here, you just see, okay, there we go. Did a tack, decided to come back to a waypoint here. And then is going to hit the waypoint, and then yeah, there we go. Start sailing downwind. So this is a real challenge to kind of get this all going together. So here's another example. This one's from out in the harbor. And so the autopilot is sailing the boat and adjusting the rudder and the sail. So how to get into this? Well, so here we got a bit of a club that races radio control sailboats, and this is really fun, kind of Saturday afternoon sort of thing, and we're able to get together. Sometimes, over 10 boats on a start line, and the racing is really, really good as far as sailboat races goes, and it's just really exciting, sailboat racing. So here's another photo. This is from another locale. Yeah, it's just a really fun thing. So here's a picture of the boats that we race. So these are regular radio control sailboats. They've just got two controls. One controls the rudder, and then another servo controls the sail. And on the bottom, they've got about 8 pounds of lead on a keel and a just regular plastic rudder, and several sails to manage different wind speeds. So, but one of the things, like I come from a background of having sailed in real boats, not these 3-foot long boats. And one of the things that was immediately apparent when we start radio control sailboating is you can't sail a radio control sailboat as well as you can a real boat. And the real, the problems are pretty basic, right? Like, because the boat is 100 meters away, and you're trying to see over there and see whether the boat's in trim, and you're not able to sail by feel, right? You can't feel the boat as it goes over waves and steer and trim as well as you can a real boat. So the basic observation here is that there is performance on the table. Like you're leaving performance on the table, and so this is kind of what I this is the genesis of this project. I naively assumed that this performance, it would be worthwhile to try and like see if algorithms and just kind of robot type approaches could sail the boat better than a human, and achieve superhuman performance, at least in the radio control sailboating world. And so, the obvious advantages of having a radio control sailboat that has a computer to sail itself is, well, you'd be able to win all the races, and of course, you'd be able to just sit on the dock and relax and, have a beer when your boat's out there taking first place, race after race. And of course, did I mention you might be able to win? Yeah, you can win. But this is a joke. The astute of you will point out that this is highly illegal, and to be clear, this is not really my real motivation. And even the sitting on the dock and relaxing part of robot sailing has yet to really haven't found that yet either. But nevertheless, it's pretty fun. But underlying this pursuit, I think, is this kind of really important question: is like robots versus humans in sailing. Could you create a boat that sailed better than a human? And this is not, this is not kind of an academic question, because there are lots of other domains where, robots can achieve superhuman performance. And so I think this is still like a really open question. But of course, I do science for my day job here, so the only way you can really get at this is to hold the boat absolutely constant, and do this kind of treatment control experiment where you pit the radio control regular human against the computer. But you have to hold the boat constant, so you can't be going and modifying the boat. All right, so that's the overarching kind of my main interest here, and let's get into it. All right, so what does this boat look like? So there's two servos, as I was mentioning. These are regular radio control servos. There's nothing special going on here. The rudder controls the steering. Some of the time, those of you who sail will know what I mean. And then there's the second servo controls the sail, and it's approximately analogous to the gas pedal, kind of some of the time. Again, those of you who sail will know kind of what I mean here. So to turn this sort of thing into a robot, what do you need? Well, you need some more stuff. So starting at the top here, you need some kind of telemetry solution to get data from the boat back to shore, and particularly when it's far away. It's not always obvious what the robot is thinking, and so telemetry is really important. The next thing is the robot, it doesn't know which way the wind is blowing. So you need a wind vane to give you your boat frame wind direction. And so that's, as I'm going to mention, it's like part of a really important control loop for sailing upwind. And the robot is kind of dumb, doesn't know where it is, so you need a GNSS or GPS to give you your position. And the robot doesn't know which way it's pointing, so you need an IMU, or inertial measurement unit, which gives you your heading and orientation and all that. And then obviously you need some kind of thing to make decisions and run your code and ideas and stuff. So there's a small computer inside the cockpit there. And really important with the robot is to have override, so the human can take control at any time. And this is really important, because the robot is, as I was mentioning, is pretty dumb. So let's get into this. What are the key kind of robotic challenges in robot sailing, and how does this kind of work, right? So the first one in my robot is this sailing the boat loop. So this is kind of directly analogous to an autopilot. So it's a control loop that steers it and trims the sails, and it runs at about 10 hertz, so 10 times a second. It takes a look at all the sensor data coming in and makes a decision about what the actual exact rudder angle should be at that instant, and what the exact sail trim angle should be at that instant. And it runs at relatively kind of basic instructions like go this direction, steer to 262 degrees, sail upwind, tack, that kind of thing. And then the next one is navigating the boat, so deciding where to go. And so this kind of is a higher level function in the robot. And it takes into account like waypoints, geofences, etc. It runs at about 1 hertz. It essentially is like an auto navigation loop that is constantly making decisions that it's passing down to the autopilot. Something that's really quite important for all robots now, and this is a really interesting area, is this idea of perception. And there's been huge leaps forward in terms of computer vision and perception. So the robot doesn't know if it's going to run into another sailboat or a buoy or a log or a seal or the dock or whatever. And so this idea of having cameras where you can identify objects in the image and figure out where they are and then come up with some sort of plan to avoid a collision, taking into account the rules of sailboat racing and all this type of stuff. This is a really hard problem. And then obviously when I'm finished this project, it's going to win every race. So there are some additional robot challenges associated with opening champagne bottles and holding, of course, giant novelty checks. And this is a joke, but I'm serious. Holding giant novelty checks is actually kind of a robot challenge. All right. So in this presentation, I'm gonna focus on sailing the boat and navigating the boat. I'm gonna just touch on kind of 2 vignettes, sort of in these parts of the boat. All right, so the first vignette I'm going to get into is looking at the wind direction measurement solution that I got going on. I use an optical wind vane, which I'll explain how it works. It's pretty interesting stuff, and sort of the remote sensing pipeline, which produces data that sails the boat. And the next one, I'm going to talk about some of the logic rules for path planning in sailboats, and talk about waypoints, geofences, simulations, and kind of some of the core challenges associated here and sort of interesting things that need to be put together to make it go. So wind direction. So as I was mentioning, when the boat's sailing upwind, it's in a control loop that's trying to hit some sort of set point in terms of the wind angle across the deck, and that's how you sail a sailboat. And so you need to know the wind direction. And so in my situation, I've got a vane made out of lightweight aluminum, and it's really important that that it's really, really low friction. And because one of the challenges here is that when the wind is very light, and this vane is not showing you the wind direction, it's just stuck because of friction, you don't have any clue which way the wind is blowing, and the sailboat basically can't function, right? So having a very low friction, fully waterproof solution is kind of like a core design requirement. So that's the vane there. And then there's a little tiny bit of red tape here. We'll get into what this red tape means and how it works and all this type of stuff in a sec. And for my my camera here, my situation, or I use a camera, so it takes pictures of this wind vane from down here, looking upwards towards the sky, and it figures out the direction the vane is pointing, and then that's how it works. So you might be thinking, well, geez, that's like a pretty elaborate way to go about this problem. And the answer to that question is yes, but it's actually been surprisingly reliable, and it gets around many of the issues. So, for example, traditional wind vane measurements are done with potentiometers. Potentiometers, to get one that's friction-free is very hard. And the other way you can do this is with an optical encoder. And again, there's just so much friction. You have to make the vane really, really big to function in low wind speeds. So this optical method actually works surprisingly well. But all right, so what happens with the pictures when they get in the camera? So they first come in like this, and this is looking upwards, so you can see that little bit of red tape. There it is right there. And so the way this works is it takes advantage of this thing where when you're looking up at the sky, the only red thing in the sky, or the reddest thing in the sky, is this piece of red tape. And so it essentially just finds the red spot in the image, and then feeds that back through. And so it starts with a raw image. In terms of remote sensing workflows, image processing, it goes to HSV, which is hue, saturation, and value, and allows you to kind of subset or threshold to parts of the image which are certain colors. In this case, we're after red. And then that gives you like a binary image, but it doesn't give you the answer. So to get kind of one answer, a quick Gaussian filter over the top of this Boolean image gives you kind of a maxima that you can work with moving forward. And there's some core constraints on sort of how fast this has to run, and it runs fast enough, but for example, some sort of neural network object detection type approach could work as well. I mean, you could detect this as an object or train it that way, but it would just be so slow. This red thing is simple and it works. So here we go. This is kind of what the pictures look like when the boat's sailing. And so this is an example. It's found the reddest spot over here, and it's negative 55 degrees, etc. Here we go, 64 degrees. This is on the other tack, and the wind's blowing at a different wind angle. And you can see the sail back here. Negative 77, negative 87. It works pretty well for kind of how failure prone it looks like from the outside. And so these are what the data look like inside of the sailboat. This is when it's on starboard tack, and so it's kind of, the boat is constantly turning to try and hit this set point of 42 degrees apparent wind. And then this, where it flops all the way over to the other side here, this is a tack, and then a tack back. And it kind of tries to dial in. This is actually pinching a bit in sort of 37-ish or whatever. This is approximately 30 seconds of data. So yeah, this is what these data look like. And that feeds straight through into the main loop that sails the boat. And what does this look like in terms of sailboating? So this is what it's sailing upwind looks like. And you can kind of catch the rudder constantly adjusting to try and maintain that wind angle set point and the trim as best as it can. All right, so next I'm going to get into navigation and this kind of traditional robot topic of path planning. I'm going to just sort of touch on a few kind of key things that I have in my navigation path planning algorithms here, but to kind of touch on the main problems that sailboats face that maybe are a little bit different than robot vacuum cleaners and other robots. So the first thing is the ocean is a big place, and so you got to kind of limit where your robot will go. Remember, it's making its own decisions about where to go, so it can make some really dumb decisions, and you want to kind of limit it. And as I was mentioning before, the perception abilities of the robot, they're just not good. The robot will sail straight into the rocks if you don't kind of geofence that area out as somewhere that the robot can't go. And I use this kind of high-level concept of waypoints within the robot to sort of get the boat to go from one point to another to try and achieve it. And then in course racing, where you're going around marks, the waypoints are the marks essentially, and the boat just kind of goes from mark to mark. So, but one of the things that's really, advantageous about robots is their measurement machines, right? So that they're producing a huge amount of data. And so there's this whole kind of ability to assimilate data that's been collected previously. So old measurements of wind, old measurements of velocity, and over the course of kind of a sailboating session, the robot can have this kind of giant database of perception of what it's felt in different parts of the course. So, great example. Often there'll be certain parts of a racetrack that will have current going one way. And so if you sail over there one time and you measure a certain kind of slow velocity over the ground from the GPS, you know that there's countercurrent, and that's not a good spot to go. And you can also pick up systematic things in the wind. So, for example, there's often certain parts of a course where the wind will come off the land, and it'll be, there'll be a higher prevalence of wind gusts from a certain direction that would be something that you should kind of take advantage of. So that leads into the whole simulation situation. And so that's where the boat takes all this previously collected velocity data and runs forward a whole bunch of potential paths. And then that rolls through to kind of this global decision about which way to go. But together, all these things get kind of ranked and put together to come up with this navigation decision. And the navigation decisions in this robot are like sail upwind or tack or sail to, course 266 or something like that. And then the autopilot is then charged with trying to achieve that direction. Okay, so what I'm going to talk now about is this waypoint and geofence thing, get into it a bit. On the relatively kind of more intuitive end of the path planning situation here. This is an island that got the robot to sail around, and these are waypoints, so started at A, B, C, D, E, all the way around H, I, J. And this polygon here is the geofence, and so you can see it traces the edge of the land, and the robot is supposed to stay inside here and it not go outside. And within the navigation loop, there's kind of two thresholds for action, and the first one is the geofence. So that's this red line, and so that's the one that I digitize, and it essentially goes along the rocks. And in terms of how the sailboat works is if it goes outside of the geofence, like if it sails outside of the geofence, it freaks out, and it basically tries to get into the geofence, as fast as possible, as direct as possible. Priority number one is to get back in that geofence. But there's also this blue line here, and this is about a 5-meter buffer in from the geofence. The idea is when the boat goes over this blue line, it doesn't freak out and try to get back in. It kind of comes up with a reasonable plan to get back in, but not with the same level of urgency and kind of violence as if it goes outside of the geofence. So there's these two thresholds for action. The blue safety zone is where you're supposed to trigger action, but if that fails and the boat doesn't get back in and it goes outside that geofence, it gets escalated big time. So here's an example of how this works. So in this case, the boat was sailing upwind along here, and then it crossed over this blue line, and that triggered a tack, or a turn away from the blue line. This is, in terms of sailboating, this is actually like an optimum solution. So even though it looks pretty violent turning away, and not that fast, this is actually the right solution. And again, it attacks and went out here. So, yeah, this is a successful run of the safety zone. Okay, and then so the next kind of thing I'm going to talk about is kind of this steer around corners problem. So if you're at waypoint H down here and you're going to go to waypoint I, and you point your boat towards waypoint I, this is the course, you're like straight. The answer is no, you can't sail over the rocks. And so, but what you want to do in the navigation loop is to not do what some other robots do. Some other robots just kind of like go to, here, they go straight towards where they're supposed to go and they just kind of muddle their way around, right? That's real slow. You should kind of, go around the corner nice and smooth like this path shows. But the question is how do you set that up in the navigation loop, and do so kind of computationally, not too expensive. So the way it works in my robot is relatively simple, but it involves a bunch of like kind of vector GIS questions. So it draws a straight line like this towards I, and it detects that it's crossing over there's intersections between these polygons and that line. And that immediately tells the robot in the code that, oh man, I can't go that way. That's not going to work out. I have to go over the geofence, right? So this is a bad choice. And so to move forward from that, it goes, hey, how about this? So it draws another ray out here. But again, this is not good because it's going straight over these two lines. Then it tests this one and it says, hey, is this okay? And you can see it's not going over any of these geofence or safety zone lines. And what it does is yes. It goes yes, and it sets an interim waypoint kind of right at that corner. And as the boat is sailing, it points towards the interim waypoint, and then when it gets here, or along the way, it's going to be constantly recalculating. It will, recalculate the next one. And in this case, you get there, you'll be able to see waypoint I, and you'll be good to go. But this is, this is kind of the optimum solution to this problem. But to get there, it requires a bunch of kind of low-level GIS path planning questions. So yeah, this is I'm gonna wrap it up now. This has been kind of an overview of some of the interesting challenges in robot sailing. Hit me up with email or comments if you have any questions. This has been a pretty fun project, and yeah, I'll just finish off with a video of it sailing outside of the island. And these are some of my experiments to try and get the boat to surf down waves. It's kind of working, but all right. Thanks so much.